Now let's look at another example. A proposed embankment fill requires a total volume of compacted soil of 8,500 cubic feet. So total volume is 8,500 cubic feet. That is the volume of compacted soil. The void ratio of the compacted fill, void ratio was volume of void divided by volume of solids. So we want to compact soil for an embankment fill. The total volume of the compacted soil will be 8,500 cubic feet, and it will have a void ratio of 0.7. That's what we want. We have 4 borrow pits that are available as with this information. We have pits A, B, C, D, void ratio of material in each pit, and cost of bringing material from each one of these. We want to see which one is the most cost-effective option. We want to bring soil from these borrow pits, and we want to see which one will be the most cost-effective option. So, for compacted soil, we will have a total volume, which is volume of solids plus volume of void of 8,500 cubic feet. And it needs to have a void ratio, which is volume of void divided by volume of solids of 0.7. From here, we need to calculate what is the volume of solids and what is the volume of void for our embankment. So we have volume of embankment equals to volume of solids plus volume of void, and void ratio of embankment equal to volume of void divided by volume of solids. This is very similar to when we wanted to calculate volume of solids and weight of solids and weight of water in a previous example. We have 2 missing parameters and 2 formulas. So we have volume of solid plus volume of void is 8,500 cubic feet. We also have volume of void divided by volume of solids is equal to 0.7. 2 missing parameters, volume of solids and volume of void, 2 formulas. We rearrange the second formula. Volume of void is equal to 0.7 times volume of solids. And instead of volume of void here, we put 0.7 volume of solids. If we do that, now we have a new formula which says that volume of solids plus 0.7 volume of solids is equal to 8,500 cubic feet. This is 1.7 volume of solids. So 1.7 volume of solids is equal to 8,500 cubic feet, which means that volume of solids is equal to 8,500 divided by 1.7. And that's equal to 5,000 cubic feet. Then you can calculate volume of void as 8,500 minus 5,000 or as 0.7 times 5,000. And you will get 3,500 cubic feet. So for our embankment, volume of void is 3,500 cubic feet. Volume of solids is 5,000 cubic feet. Why do we need to do this? Because this will be constant. Because the question told us, assume that the specific gravity of soil solids from all of these pits are the same as embankments. So assume the specific gravity of soil solids to be the same at all pits. What does that mean? It means that we need to bring the same amount of solids from all of these pits. Because they have different void ratios, we cannot use the total volume. We cannot use the 8,500 cubic feet because they all have different void ratios. But we can use volume of solids. In our embankment, we need 5,000 cubic feet of solids, which means that we need 5,000 cubic feet of solids from each one of these pits. So, for example, pit A, we need to have, let's look at pit A. We need 5,000 cubic feet of solids. Void ratio is volume of void to volume of solids. So if we need 5,000 cubic feet of solids, then volume of void is 1.08 times 5,000. So volume of void is 5,400 cubic feet. So for soil A, we still need to bring the volume of solid is the same, 5,000 cubic feet. But since void ratio of A is 1.08, it means that volume of void will be 5,400 cubic feet. So our total volume is 54 plus 5,000, which is 10,400 cubic feet. So that's how much material we need to bring from pit A to make sure that there is 5,000 cubic feet of solids to be able to do the 8,500 cubic feet for the embankment fill. We also know that it will cost $5 per cubic feet. So the total cost is 10,400 cubic feet times $5 per cubic feet. So the total cost to bring material from pit A for our embankment fill is $52,000. Now we're going to do the same thing for pit B. Again, we need to have 5,000 cubic feet of solids from B. For B is 0.85, which is equal to volume of void to volume of solid. So volume of void for pit B is 85 times 5,000. Which gives us 4,250 cubic feet. So now for soil B, again, volume of solids is 5,000 cubic feet. Void ratio is 0.85. From here, we can calculate that volume of void is 4,250 cubic feet, which means that the total volume is 5,000 plus 4,250, which is 9,250 cubic feet. That's how much material we need to bring from pit B to make sure that we have enough solids for our embankment. This one, the cost is $8 per cubic feet, so the total cost is $74,000. You need to repeat this for pit C and D. Again, for both of these, for pit C, and pit D. Volume of solids is still 5,000 cubic feet. Void ratio in pit C is 0.87. For D is 0.80. We do the calculation for volume of void. Here it's going to be 4,350 cubic feet. And here it will be 4,000 cubic feet. So we have a total volume from pit C as 9,350 cubic feet. Cost is $9. And then here we have total volume of D is 9,000 cubic feet. Cost is $12. So we have and then we can compare the results and see the most cost-effective option is to bring material from borrow pit A. Exercise number 3, it's from compaction. So we have the results from laboratory results of a standard Proctor test. We have volume of mold. So we have this mold. Volume of mold is 1/30 of a cubic feet. And that's equal to volume of compacted soil. We compact our soil in here. And we also have weight of moist soil. So weight of moist soil is weight of soil, compacted soil in here. So we also have weight. This will be volume of compacted soil. And this is weight of our compacted soil in the mold. When you divide weight by volume, you can calculate moist unit weight. So moist or wet unit weight is equal to weight of compacted soil divided by volume of compacted soil. So for example, look at trial number 1. Weight is 3.82 pound, volume is 1/30 of a cubic feet. We will have 114.6 pound per cubic feet. Then we need to calculate dry unit weight. Gamma D, which is equal to gamma, this is gamma, divided by 1 plus water content. So it's going to be 114.6 divided by 1 plus moisture content is 10% or 0.1. That will give us so that's trial number 1. You need to repeat that for trial number 2, 3, 4, 5, and 6 to complete your table. When you have all of the numbers that you need, you use these 2 rows. Water content is your x-axis, and dry unit weight or gamma D is your y-axis. You make your curve and then find peak of your curve that gives you optimum water content in percentage that yields maximum dry unit weight, which is also the maximum level of compaction.